Okay guys, so today we're going to start our new unit on chemical equations and chemical reactions. So today we're going to look at chemical equations. Next class we're going to look at balancing chemical equations. Then we will have a quiz on chemical equations and balancing chemical equations. And then we'll start our next section on types of chemical reactions. So, chemical reactions and equations. What is happening in this picture? How would you explain what is happening with the chemicals in this picture? A chemical reaction is a process that involves the rearrangement of the atoms in reactant molecules to form new molecules, which are referred to as products. A chemical equation is a shorthand way of communicating the reaction that is occurring. A chemical equation packs a great deal of information into relatively few symbols. So what a chemical reaction is that one thing or more than one thing will rearrange itself to create new things. So the reactants are the ones that are rearranging themselves to create the product. So reactants react to produce products. Now, according to the law of conservation of mass, the total mass of reactants must equal the total mass of the products for any given chemical reaction. The law of conservation of mass tells me that matter can neither be created nor destroyed, meaning that I must have the same number of oxygens that I start off with and the same number of oxygens that I end up with. If I start with 4 oxygens on the reactant side, I must have 4 oxygens on the product side. If I start off with 2 hydrogens on the reactant side, I must have 2 on the product. And so it's incredibly important that we follow this law of conservation of mass. That's what we're going to be doing next class when we're balancing reactions or balancing chemical equations. So parts of a chemical equation. So this is an entire chemical equation. So we have 2H2 plus O2 gives us 2H2O. Now we'll see hydrogen and oxygen are written with a subscript of 2, and that's because they are diatomic elements, and we'll talk about that in a second. So chemical formula is a symbolic representation that uses element symbols and numbers to show the composition of a chemical substance. So a chemical formula tells us what the substance is made of and how many atoms of each element we have in that substance. A subscript is used to show the number of each type of atoms in a chemical substance. So the subscript tells us how many of each type of atom we have in that chemical substance. Then we have our reactants. So on our reactant side, we have the chemical substance that is present at the start of the reaction. So in this case, H2 and O2, those are present at the beginning. The reactants are what is present at the beginning of the reaction. The reactants can be found on the left side of the arrow in a reaction. Now, products is the new substance that is formed during a chemical reaction. So products is the new substance that's formed from the reactants when the reactants rearrange themselves. And you can find the products on the right-hand side of the arrow. Now, a coefficient is a number written before a chemical formula to show how many molecules or moles are present. Don't worry about moles right now, but what a coefficient does is it helps us to follow the law of conservation of mass. It helps us to equal out the numbers of hydrogens and the numbers of oxygens in a chemical reaction. So notice here that we have 2H2. Now these coefficients are going to multiply. Okay, so 2 times 2 hydrogens gives us 4 hydrogens. Now oxygen, we don't have a coefficient. That's going to be understood as a 1. Okay, and that means I have 1 O2, which means I have 2 oxygens. Now that we have a 2 in front of water, again, the 2 is going to multiply to that 2, and that's going to give us 4 waters. And then the 2 is going to multiply to that 1 oxygen, and that'll give us 2 oxygens, okay? So in this equation, we have 4 waters and 2 oxygens on each side of the equation. That's what we want. Remember, we can't just, a hydrogen can't just disappear when a reaction occurs. Now, how do we tell that a chemical reaction has occurred? There are some observed changes that we can use to tell if a chemical reaction occurred. So the first one is the evolution of energy as heat and light. If something gets hot or if something gets cold, then that can tell us that it is a reaction has occurred. And if something lights up, that means a reaction has occurred. Production of a gas, if something is bubbling, that means a reaction has occurred. Formation of a precipitate, that is a solid that is produced as a result of a chemical reaction in a solution. That will tell us if a reaction has occurred. So what happens with a precipitate is you have two liquids, you have two solutions, and when you mix those two solutions, it forms a solid. Now, it can either form a solid such as like a gel, or it can form a solid in the solution, which makes that solution opaque, meaning you can't see through it, kind of like milk. Now, number 4 is the change in color. So if it changes from clear to yellow, or if it changes from green to blue, that will show us that a chemical reaction has occurred. Now, these are different characteristics of chemical equations. You will see these within chemical equations, and it's important that you understand what they mean. So if you see the symbol S in parentheses, that means that a solid or a precipitate is there. So if you see sodium, Na, with an S next to it, that means we're looking at solid sodium. Now, this is an L, okay? So if you see an L next to it, that means that this is a liquid. So water would be an example that it would, if you're using water in a liquid state, it would have an L next to it, but if you're using ice, then it would have an S next to it. Now, G means it's going to be a gas. Now, AQ means aqueous. So remember, aqueous, aqua means water, so aqueous means dissolved in water. That's going to come important when we're talking about types of chemical reactions. Now, you'll see this double arrow. That means that the reactions go both ways. That means that you can have a forward reaction going from reactants to form products, or you can have a backward reaction, meaning the products break down to form the reactants. Now, if you see a symbol of this triangle, which means delta, or if you see heat, it's kind of hard to see, heat above an arrow, that means that heat is needed for a reaction to occur. And so that means that we need to heat something up for that reaction to occur. Now, if you see an arrow and you see a PT before that arrow, that means that a catalyst is needed. Now, catalysts, you've probably heard of them in biology. A catalyst speeds up a reaction. So an example in biology you probably heard of is an enzyme. An enzyme binds to certain proteins to make those proteins react. Now, diatomic elements. So remember when we were looking at our chemical equations, I said that hydrogen and oxygen are diatomic. What that means is that when elements exist by themselves, okay, this does not mean if they're in water, because notice water is H2O, even though oxygen is diatomic. So if they're existing by themselves, meaning if I just have hydrogen, if I just have oxygen, if I just have nitrogen, they're going to exist bonded to one another. And so their molecular formula is actually going to be with a subscript of 2. Now, these you just have to memorize. If you look on the periodic table, you'll see hydrogen in its corner. And then if you go over to nitrogen, you'll see it forms a 7. The elements that are diatomic forms a 7 on the periodic table. So it's nitrogen, oxygen, fluorine. That's the top of the 7. Then chlorine, bromine, iodine. That's the long side of the 7. Okay, and those are all the diatomic elements. So hydrogen plus nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Now, let's talk about different types of equations. So a word equation is changed to a symbolic equation to show us what happens to the substances that are involved in a chemical reaction. So a word equation is an equation with just words, hence the term word equation, that tells us what's reacting and what's being produced. Now, a word equation is qualitative, meaning that it doesn't have numbers or anything, it's just descriptive. Now, the first step in writing a correct chemical equation is to replace the names of the reactants and products with appropriate symbols and formulas, okay? So this is where all of last unit has gone into it. That review we did last week, this is where it comes into play. So we have a word equation and we want to write the formula equation. We want to write those formulas. And so we have to use our rules for nomenclature that we've been learning to do this. So a formula equation represents the reactants and products of a chemical reaction by their symbols and formulas, okay? So here's an example. This is a word equation. It's in words. Methane plus oxygen yields carbon dioxide plus water, okay? Now, this is a formula equation. Those are formulas, right? They're letters and numbers. So methane, CH4, plus oxygen, O2. Now notice oxygen is written as O2 because it is a diatomic element. So oxygen, again, notice is by itself. It's not bonded to anything. The only time you write it as diatomic is when it is by itself. Now that's going to yield carbon dioxide plus water. So carbon dioxide is a covalent compound, so we use those prefixes, so CO2, plus water. Now you should know at least know the formula for water, which is H2O. And again, notice that the oxygen here is no longer diatomic. The hydrogen here is diatomic to bond with that oxygen correctly. Now the second step in writing word and formula equations is balancing the equation. This is what we're going to do next class. But the next step in the process of writing correct equation, the law of conservation of mass must be taken into account. So the relative amounts of reactants and products represented in the equation must be adjusted so that the numbers and types of atoms are the same on both sides of the equation. We must have, if we start off with 6 oxygens, we must end up with 6 oxygens. If we start off with 3 hydrogens, we must end up with 3 hydrogens. And so to do this, we put coefficients in front of formulas to help us balance that out, okay? Now again, coefficients go in front of each substance and they're going to multiply. So if I have 2 H2O, then 2 times 2 hydrogens gives us 4 hydrogens, and then 2 times 1 oxygen gives us 2 oxygens. So to change word equations into formula equations, follow the flow chart. So we got another flow chart. So you look at what is given to you. Now in word equations, you have, again, if we have methane plus oxygen, okay? You have to look and see, that's not a good example. Let me do something else. Let me do, we'll do sodium chloride, okay? Sodium chloride plus oxygen. We first have to determine if it's an element or a compound. Now, every time you see a plus or an arrow, it's starting over this process of asking if it's an element or compound. So sodium chloride is a compound, 2 words, right? Oxygen is an element, 1 word. So if it is an element, the next question you have to ask yourself, is it diatomic? So looking at oxygen, is oxygen a diatomic element? And again, you just have to memorize those. The answer is yes. So if the answer is yes, then you're going to put it as a subscript of 2. So notice that oxygen is O2. And again, this is only if oxygen is by itself. If it's in a compound, you do not do this. Now, if the answer is no, then you do not put a subscript and you just write the element symbol. So sodium is not one of those diatomic elements. And so you're just going to put the symbol for sodium, which is Na. Now, if the substance is a compound, okay, if it's more than 1 word, or a common compound like water, then you have to ask yourself, is a compound ionic, covalent, or an acid? So looking at this compound, looking at sodium chloride, I see that sodium, again, to determine if it's an ionic, covalent, or an acid, if it's an acid, it ends in acid. It tells you. Ionic or covalent. Ionic, remember, is a metal and a nonmetal, whereas covalent is 2 nonmetals, right? Well, here, sodium is a metal, therefore it's an ionic compound. So if it starts with a metal, it's ionic. If it starts with a nonmetal, it's covalent. So an ionic compound, what we have to do is balance the charges. So here's another example, sodium oxide. So we have to balance the charges of sodium. Sodium has a positive 1 charge. We got that from the periodic table. Oxygen has a negative 2. We got that from the periodic table. And when we balance those, we want to make sure that the positive and negatives cancel out. So we add another sodium, and that'll give us Na2O. Now, if we have a covalent compound, we use those prefixes. So here we have prefixes in front of them. Tetra means 4, so 4 sulfurs, and tri means 3, so 3 iodines. If the compound is an acid, then we use the ending or beginning to name it. If it starts with hydro, that means it's just the nonmetal. And again, acids are balanced out with hydrogen positive 1. So it's hydrogen positive 1 balanced out with the negative charge. So if it starts with hydro, that means that the negative charge is just the nonmetal. If it does not start with hydro and ends in ic, then it's an 8 polyatomic ion. If it does not start with hydro and ends in us, then it's an 8 polyatomic ion. So looking at this first example, iron plus oxygen gives us iron 3 oxide. Now I like to draw parentheses around each one, okay? Now I know to start over if I have a plus sign or an arrow, I start over, okay? So my first one is iron. Now iron, element or compound? Iron is an element, okay? So our next question is it diatomic? Iron is not diatomic because I memorized my diatomic elements. So when I'm writing iron, I just write its atomic symbol. Please write the correct atomic symbol. Please, 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 okay? Now, what you're going to do is just bring down that plus sign. We are not combining iron and oxygen because what's happening is iron and oxygen is already combined on our product side. We're just writing it out as their symbols. Now, our next one is oxygen. Is that an element or a compound? Oxygen is an element. So our next question is it diatomic? Yes, which means when I write oxygen, I'm going to write it as O2, okay? Now bring down that arrow. Iron 3 oxide. Iron 3 oxide, element or compound? It is a compound. It's more than one word. So our next question is it ionic, covalent, or an acid? Well, it doesn't end in an acid, so I can don't have to worry about that. Now we're looking at ionic or covalent. Look at that first word, iron. Is that a metal or a non-metal? Iron is a metal, so it is going to be an ionic compound, okay? If it's an ionic compound, that means we have to balance some charges. So iron 3, what that 3 means is that the iron has a positive 3 charge, okay? Now oxide, if it ends in IDE and it's not hydroxide or cyanide, then it's just the element. So oxide means it's just oxygen. I'll look on my periodic table, I see oxygen is a -2 charge. Okay, so I'm balancing out iron positive 3 and oxygen -2. Now remember, we want these overall charges to be the same, right? So I'm going to add another oxygen, -2. That gives me a -4. But they're still not the same, so I'm going to add another iron, positive 3. And that gives me positive 6. Still not equal, so I'm going to add another oxygen, -2. And that gives me a -6. So now we have a positive 6 and a -6, so we're going to write the formula for that. We used 2 irons, so it's going to be Fe2, and 3 oxygens to balance that out. So Fe2O3. There's my formula equation. Now let's look at some other examples. So we have sodium chloride. So again, I'm going to put parentheses around each one because each one is its own kind of little problem. So first one, sodium chloride, element or compound? It's more than one word, so it's a compound. Now, is it ionic, covalent, or an acid? Doesn't end in acid, so it's not an acid. I see that it starts with sodium, which is a metal, which is an ionic compound. So we have to balance charges. So sodium's charge, if I look on my periodic table, is positive 1. Chloride, that is chlorine, -1, okay? Because I know that if it ends in IDE, it's just the element, so it's chlorine -1. So my formula is going to be NaCl. Plus, now fluorine. Fluorine, just an element. It's just one word. It's just an element. Is it diatomic? Yes. So I'm going to write it as F2. Okay, bring down that arrow. So again, we're bringing down those plus signs and those arrows. Sodium fluoride. Now, element or compound? It is a compound, not an acid because it doesn't end in acid. Let's see, it starts with sodium, which is a metal, so it's an ionic compound balancing charges. Okay, so sodium's charge is going to be positive 1. Now, fluoride ends in IDE, so I know that's just fluorine. And it's going to, if I look on the periodic table, it has a -1 charge. I don't need to add any sodiums or fluorines to balance out any more charges. So our formula is going to be NaF. Okay, bring down that plus. Now, chlorine. Chlorine's just an element. Is it diatomic? Yes. So I write it as Cl2. So one thing I want to point out with this formula equation, notice I have 2 fluorines on my reactant side, but I only have 1 fluorine on my product. So that's what we're going to be doing next class is we're going to use coefficients to balance out every single compound in this reaction. Now the next one, aluminum plus sulfur yields aluminum sulfide. Okay, so aluminum, element or compound? It is an element. Is it diatomic? No. Aluminum is not diatomic, so we're going to bring it down, just write its symbol. And again, please note these symbols. Do not write S for sodium, because that is going to be sulfur. So moving on to sulfur. Sulfur is an element. It is not diatomic, so I'm just going to put S. Bring down that arrow. Okay, sulfur, S means sulfur, not sodium. Sodium is Na. You've got to know these. Now, moving on, aluminum sulfide. It is a compound. It's not an acid. Doesn't end in acid, so it's not an acid. Look at what it starts with, aluminum. Is that a metal or a non-metal? Aluminum is a metal, and so it's going to be an ionic compound. So we got to balance some charges. We got aluminum, +3, and I got that from my periodic table. Sulfide ends in IDE, that's sulfur, -2. So I have aluminum, +3, and sulfur, -2. So to balance those charges, I'm going to add one more aluminum to make that +6, and 2 more sulfurs to make that -6. So when I'm writing my formula, it's going to be Al2S3. Okay. Now, my last one. Zinc sulfide plus magnesium phosphate yields zinc phosphate plus magnesium sulfide. Okay. So, our first compound. Now, looking at all of these, I see that they're all compounds. So I'll look at the beginning of each one, and I see that they either begin with zinc or magnesium, which are both metals. So all of these are ionic compounds. Okay, so I'm going to balance all the charges for these. Now, zinc. Zinc is a transition metal, but I'm not given a Roman numeral. If you look on your periodic table, you'll see that zinc, in the little corner, you'll see it only has one charge, and that's a +2. So zinc is only a +2 charge. Now, sulfide, IDE, that's just sulfur, and that's going to have a -2. So I have zinc +2, sulfur -2. So my formula is going to be ZnS. Bring down that plus sign. Then I have magnesium phosphate. Magnesium, I look on my periodic table, is Mg +2. Phosphate is PO4. This is a polyatomic ion, ends in 8. Polyatomic ion. PO4 -3. So to balance those out, I'm going to have 3 +2 magnesiums and 2 -3 phosphates. Okay. Now zinc phosphate. Zinc we said was +2. Phosphate was PO4 -3. And so my formula is going to be Zn3. So 3 +2 charges and then 2 -3 charges. Okay. Then my last one, magnesium sulfide. Magnesium is a +2. Okay, Mg +2. Sorry. And then sulfide, again, IDE, that's just sulfur, -2. So that's going to be NgS. Okay. So I'm going to skip the last 2 examples on the PowerPoint, but this is how you write word equations. This is how you write formula equations from word equations. So again, you'll have a quiz on this 2 class periods from now, so please be studying for that quiz.